Number 11, 12, and 13. String is wrapped around a pulley. Here's the string. It's wrapped around this pulley. A 150-gram mass is suspended from the string, held at rest, and then allowed to fall 0.4 meters. The mass falls the 0.4 meters in 2 seconds. So to go from here to here takes 2 seconds. It's starting from rest. The first question is to find the mass's linear acceleration during its fall. And this is the formula to use. We know the displacement, that's the height that it falls. We know the initial velocity is 0, so v0t ends up being 0. We can ignore this. And 1/2 at squared, we're actually looking for a. We know the time. The time was 2 seconds. Now, we can make the acceleration positive or negative here. I've chosen to just call this distance a positive 0.4 meters, even though it's downward, and then I'm going to get a positive acceleration. You could do this like the books tell us to. You could have negative there and get a negative acceleration. That works too. But I think it's simpler this way. So we have 0.4 meters equals 1/2 a times 2 seconds squared. 1/2 times, well, I should work some of this out. 1/2, 0.4 meters equals 1/2 times a times 4 seconds squared. 0.4 meters equals 2a seconds squared. And then I can divide both sides by 2. And I'm going to divide both sides by seconds squared. So now the seconds squared cancel out on this side. The 2's disappear over there. And I'm left with 0.4 divided by 2 seconds squared, which gives me 0.2. 0.2 meters per second squared equals a. So there's the solution. Number 12 is asking for the kinetic energy at the bottom of its fall. Here's what I've written in the solution. The mass does not spin, so the kinetic energy of the mass is just 1/2 mv squared. We need the velocity at the bottom. So this is just falling straight down. There's no rotation to it. When it gets to this point, it's moving faster. It's been accelerating the whole time. We can figure out its velocity, and from its velocity, then we can use kinetic energy equals 1/2 mv squared. So here's a formula that will help us. Velocity equals v0 plus at. In this case, the initial velocity was 0. So we just have, instead of v0 plus at, we just have v equals at. The acceleration we figured out in the previous problem. This was accelerating downward at a rate of 0.2 meters per second squared. So we have velocity, that final velocity, equals 0.2 times 2 seconds. That's the amount of time that it was falling. Multiply them together and you get 0.4 meters per second. That's the final velocity when it's right here. To figure out the kinetic energy, we have to use 1/2 mv squared. So 1/2, there's the mass. 150 grams is 0.15 kilograms. The conversion, grams to kilograms, there are 1,000 grams. 1,000 grams equals 1 kilogram. So if you want to go from grams, you need to divide by 1,000. To make all the units work out nicely, you can say 150 grams divided by 1,000 grams per kilogram. The grams will cancel out, and you'll get 0.15 kilograms. So there's the velocity at the end. Got to use the final velocity, square it. When you square this, and then multiply it by this, and then multiply it by half, you get 0.012 joules. For number 13, this is the tricky one. The pulley. What is the pulley's kinetic energy when the mass reaches the bottom of its 0.4 meter fall? In order to figure this out, we can use conservation of energy. In the beginning, the mass was here, nothing was moving. So everything, all the energy that this whole apparatus had was this potential energy, which was just mgh. Now, by the time that the thing gets here, let's just call this 0 elevation to make things easy. P equals 0. So none of that potential energy is left. All of that potential energy has turned to other things, one thing being motion of this. We just figured out how much energy this has. So the rest of that potential energy must have gone into spinning the pulley. So all we really need to do is figure out the potential energy in the beginning, subtract this kinetic energy of, translational kinetic energy that we just calculated, and that'll give us the kinetic energy of the pulley. Now, what did I write here? This looks complicated. Oh, but it's not. So I just wrote that. I wrote it all out. PE1 of the mass equals KE2 of the mass plus KE2 of the pulley. And that's what we're looking for. This is the only energy at the beginning. It's mgh. This is 1/2 mv squared. And this is the one we're looking for. So we have mgh equals KE2 plus KE2 for the pulley. mgh 0.15 kilograms times 9.8 meters per second squared. That's g times the height, 0.4 meters. I didn't show it here, but I got some kind of number here, and the units were would have been joules, some number of joules, and that equals the kinetic energy of the mass. That's what we figured out from the previous question, falling mass, plus the kinetic energy of the pulley. So whatever this number was, when I multiplied it all out, I had a number over here. I then subtracted this from it, and that gave me KE2 of the pulley. So this is a fairly simple thing to do algebraically. I don't feel like I need to show you that. Hope that's okay.